Hi everyone, I'm very happy to be here today to present this survey on spatial interfaces for 3D visualization. I would have been happier to make this presentation live and go for some drinks with friends after, but we have to adjust to the pandemic situation unfortunately. Anyways, this paper is the result of a collaboration with Anders Innemann, Lingwen Yu, Daniel Keith, and Tobias Eisenberg, and myself of course, Lonnie Besançon. I think all of these photos were taken pre-COVID, and looking at what lockdown has done to me, I'm not sure you can trust these mugshots too much. But anyway, I would argue that there are a couple of terms that we have to clarify from this title. And that's what we mean by spatial interfaces and what we mean by 3D visualizations. So the first thing to clarify is what we mean by 3D visualization. We essentially mean all tasks involved in the sense-making process of 3D datasets that are omnipresent in a variety of fields such as architecture, 3D printing softwares, spatial dataset exploration, medical datasets, and many others. I will not try to make an exhaustive list here. But what is so particular about 3D visualization is, well, that unlike 3D interaction, the goal of 3D visualization goes beyond simple 3D manipulations that have been a huge focus of research in the HCI community. It should include and support more tools for users to be able to understand and derive insights from the data, such as cutting plane manipulation, specific widget placement, or 3D selection of volume of interest. For instance, you can see here a fluid dynamic researcher visualizing a cut through a 3D dataset and manipulating setting point placement in a volume to understand the flow in the original dataset he is looking at. But if you hear 3D interaction and perhaps even 3D visualization, you might think, yet another survey paper on 3D techniques, and it's true that 3D interaction has been the focus of many surveys in the past. However, none of them quite address the focus that we have set out to present today. Let's quickly review why. This survey by Chris Hand was published more than 20 years ago and solely focuses on 3D interaction techniques. So it's quite obviously not up to date, but it also does not address the specific challenges and needs of 3D visualizations. Christian Oliver's work is now 15 years old and only focuses on camera control. Much like other 3D interaction techniques, and the survey focusing on them, camera control is useful for 3D visualization tasks, but it is not sufficient. Some survey did focus on interaction for data visualization, but they focused, for instance here, with Peniel and Roberts' survey, on a single interaction paradigm, which is here haptics. While the survey here focused on meter gestures. This other work by Jankowski and Ashe is more recent, but focuses only on 3D interaction techniques and not on visualization needs in particular. And the same thing can be said about the survey by Mendes et al., who focused on object manipulation. This is again needed for 3D visualization tasks, but not sufficient. Finally, this last survey focused on medical flow data, which is a specific kind of dataset that is related to 3D visualizations, but the survey does not explore how interaction can help in that regard, and instead focuses on data generation and its analysis. Now it's time to explain what we mean by spatial interfaces. We basically mean paradigms that help propose 3D techniques for 3D interaction, such as tangible interaction, touch interaction, or media gestures. We also include combinations of these paradigms together. Now, why do we focus on these? Well, as I said, a myriad of techniques for 3D interaction have been developed with these, but also they are readily available with off-the-shelf devices, such as mobile devices or simple infrared cameras. Mobile devices can even already be used as a combination of touch devices and tangible devices. But before we dive into the heart of the survey, let's quickly check why these interaction paradigms are interesting. Touch interaction first. It is precise, it is fast, it gives a feeling of direct manipulation, and can be augmented with pressure sensing or multi-touch interaction to provide a richer interaction technique. Tangible interaction now. It is fast because it mimics the way we interact with the world in real life, it has specific understanding value, and it is good for collaboration scenarios. Devices have to be either optically tracked with a proper dedicated camera, or the camera of a mobile device that you can see here, or it has to contain some sort of internal sensors in order to manage to locate itself, just like some mobile devices now do by combining the camera and internal sensors. With mirror gestures, which also mimic the way we interact in the world since movements are inherently 3D, one of the great advantages is that hands are kept free, which is useful in some specific scenarios, such as the one of an operating room that we can see here. Tracking of the hands is either passive with optical tracking, as you can see, or it can be active, as visible here with a specific hand-worn device such as a glove. We finally consider hybrid interaction paradigms. You can see here a combination of touch and tangible interaction, for instance. It helps alleviate the inherent drawbacks of each single interaction paradigm and combine the benefits. So these interaction paradigms are the first axis that we use to categorize the work we surveyed on spatial interfaces for 3D visualization. But what is the other one? We decided to look at visualization tasks to categorize each paper we surveyed. Why is it important? Because it would allow us to see if a specific subcategory of task has not received enough attention, for instance. There are once again many papers proposing classification of tasks in EuroVIS or 3D interaction. However, they do not really consider that 3D visualization does introduce some special requirements for interaction tasks, as rightfully pointed by Keith and Eisenberg. As we mentioned earlier, simple manipulations are not enough. To understand, for instance, the internal structure of a dense volumetric dataset, as we can see here, right? Similarly, 3D object selection techniques are unlikely to help researchers select line in a dense 3D dataset such as this one. So what tasks did we focus on? Well, first we consider the essential task of view and object manipulation. So a single viewpoint is rarely enough to properly analyze and understand a 3D dataset, consequently offering the possibilities to manipulate either the viewpoints or the dataset to offer several perspectives becomes essential. But beyond this, many 3D datasets suffer from occlusion. The internal structure of the data is initially not visible to domain experts. So instead of focusing it only on object manipulations, such as the one used in HCI, this task that we decided to have includes also cutting plane manipulation that will help reveal the internal structure and properties of the data. Beyond simple object manipulation, scientists looking at 3D datasets have been reported to often make use of axis-constrained manipulations. So we report in this survey whether techniques allow for such constrained manipulations or not. Simply looking at the data is often not enough for domain experts. They often need to rely on specific widgets to explore the data beyond cutting plane and internal structures. Scientists make use of many different widgets. You can see here sitting points that are basically weightless particles that will follow the flow within a dataset in order to help scientists understand vector fields within the data. Many other widgets exist, and their use is essential to explore 3D datasets in many different fields. That is the second task we focus on. Finally, the last task we consider is 3D selection and annotation. 3D selection techniques developed by the HCI community, as we earlier mentioned, are unlikely to work in molecular visualization or dense line datasets. Very often, HCI techniques help select a single object, and you can imagine that selecting atoms one by one would be a very tedious process. We link annotation to this task because it either requires the annotation to be positioned in 3D or it is attached to 3D selection very often. So this finally constitutes the two axes that we use for our survey. We surveyed a total of 134 techniques that we found with a Google Scholar search and following trails of citations. So now I'll try to give you a quick overview of the papers we have found and some of the interesting techniques and findings from there. Let's start with touch interaction. We have a total of 33 techniques that we found with our survey. If we consider the first task of view and object manipulation, we found 90 techniques that allowed it. One of the issues with touch interaction is that it is inherently 2D, while we want to be able to manipulate objects in 3D. That includes rotation around all axes, translations along all axes, and sometimes zooming as well. The HCI community solved this issue with the help of different mappings, such as the following one. Two fingers manipulation are used for X and Y translation, and they are also used to provide Z translation, which can be assimilated in some cases to a zoom operation with the pinch to zoom technique that is now very common on smartphones. One finger manipulations are mapped to XY rotations, and finally rotations around the Z axis are provided with two fingers as well. But what has been done for specific visualization purposes? One technique we used a lot in visualization project is the T-box technique, which is a widget to facilitate 3D manipulations with multi-touch gestures. One-finger manipulations along the edge of the cube translate along the parallel axis. One-finger manipulation on the side of the cube controls single-axis rotations. Scaling is controlled by pinching the cube. Other techniques have used the 3D axis in the scene to help define axis-constrained interaction. For instance, a two-finger touch was used to define an axis along which subsequent manipulations would be constrained. Here you see the FI3D widget, which is another widget to provide such manipulations. So translations around the XY axis are initiated with a single finger interaction in the central space. XY rotations are initiated with a single finger touch on the frame and a drag into the center visualization region. Touching the frame with a second finger during this interaction constrains the rotation to single axis depending on the frame. Rotations around the Z-axis are controlled by dragging a single finger along the frame. Some researchers also focused on providing dataset-specific interaction technique. You see here the power of 10 ladder technique. It facilitates exploration of astronomical datasets, which require rotation and scaling operation that span large magnitudes. Two-finger input activates a ladder widget, where each region corresponds to a power of 10 zoom level. The technique also provides classic panning with 5 fingers and rotations with 1 finger. Overall, we find quite a lot of different techniques relying on different widgets or specific gestures to provide 3D manipulations. What has been done for visualization widgets manipulation now? The problematic thing about visualization widget is that they need sometimes to be positioned in the 3D volume. When they don't, such as for drilling cores positioned at the top of a topological map, simple gestures or widgets are enough. When 3D positions are needed, things get more complicated. The technique you see here relied on a combination of gestures and a dual view. The view on the right is the unprojected view from the cutting plane that is positioned on the left. Experts can use the view on the right hand to position visualization widget onto the cutting plane that is in the dataset. The position of finger give the XY positions at the intersection with the cutting plane provide the depth information that is missing from touch interaction. We only found 3 techniques that propose to have visualization widget manipulations with touch. What about 3D selection now? Again, the third dimension is missing, and that's a bit problematic, but research work has found ways around it. One way around this issue is to rely on a computer to provide the third dimension. Let's imagine that the user draws a lasso to select a part of the dataset. The computer can simply extend the lasso into 3D, but this might also select parts of the data that are not of interest to the user. So more sophisticated approaches have been designed which rely on the properties of the data to assist the user into making a selection volume from a 2D lasso. You can see one of them being used here that rely on the density of particles to provide a selection. If there is some void between two objects that would be selected by a simple 3D extrusion of the lasso, the technique is smart enough to not consider the other object, because it relies on the viewpoint use and the property of the visualized data. An alternative is to rely on several steps, which will produce a selection based on the viewing angle, the structure, and the slice of the data that is shown. Most of the techniques we have found rely on the properties of the data to facilitate 3D selection and overcome the 2D nature of touch input for selection. And overall, touch input is mainly limited by its inherent 2D nature. It has been overcome with specific techniques that are often, however, data dependent. Still, touch interaction provide fast and precise manipulation, easy access to widgets and menus, and has naturally constrained manipulation which are often helpful for 3D visualization. It was therefore the focus of a variety of research papers. It is actually the second most investigated paradigm among the papers we surveyed. Now on to tangible input. We said earlier that tangible input is great to mimic live interaction and has therefore been the focus of a lot of work for 3D manipulation in HCI. How has it been used to help visualize spatial datasets? First, let's look at data and cutting plane manipulations. Since the pioneer work of Hinckley and colleagues in 1994, many specific tangible props have been designed to assist the manipulation of data and cutting planes. Some decide to use props representing the data to visualize, as you can see here. The benefit of using a prop representing the data itself is that the prop can give users a sort of world in miniature version of the data, and all the manipulations of the props are simultaneously happening in a digital world. Other approaches just use more generic props to avoid having to generate many different props for many different datasets. Here you see a pen being tracked by the tablet to help manipulate the cutting plane of the data that can be manipulated with the cuboctahedron that you see in the background. And specific AR and VR environments controllers developed with commercially available software can help serve as tangible controllers that are very versatile and generic. Interestingly, props like paper can also be used to see different views of the data through their manipulations. You see here that the paper-like prop is used to navigate between different anatomical views. One of the nice advantages of tangible interaction is that it can allow concurrent manipulation of either multiple parts of the data or of data and cutting planes at the same time, for instance, as you can see here. Another one is that users can use tracked flexible materials to provide non-planar so-called cutting planes of the data. Some tangible devices also facilitate less visual-oriented exploration tasks through active haptic feedback. For instance here, haptic forces are used to represent and simulate molecular interactions. There are really quite a lot of approaches for data and cutting plane manipulation, even more than with touch input. But what about visualization widgets now? We have found a couple of techniques that are proposing some of these. Most of them rely on pointing, either with a specific or generic device, to the 3D location where the widget should be placed. In this first example, the pen allows users to do it. And in this example, the author used a Wiimote, the self-track controller from the video console Wii from Nintendo, to position a seating point. While in this example, the author allowed the placement of trim ribbons to explore and understand the vector fields of flows around an aircraft with a phantom device, in order to benefit also from the haptic feedback of the device to help guide exploration and positioning of the ribbons. We still did not find a lot of different techniques supporting what we call visualization widgets. How about 3D data selection and annotations now? Devices providing haptic feedbacks have been studied and seem particularly interesting for selection in dense datasets, for instance. They can also allow users to draw selection shapes in 3D directly from which the selection volume will be derived. More generic props can also be used, as you can see here, with basic AR markers moved around to help select part of a brain. In many cases, the track prop can also directly propose to annotate selection through direct manipulation. While this might not be ideal for note-taking, for which it's usually easier to have a plan to write on, it is particularly interesting to draw some annotations and sketch some input or ideas. Tangible interaction was overall the most investigating paradigm that we found. This can probably be explained by the inherent 3D nature of tangible devices that seem to make them, at least in theory, very well suited for 3D visualization tasks. Now let's tackle meter gestures. Meter gestures are particularly suited for some specific domains that require hands to stay free or sterile, such as surgeries and medical applications. While moving hands is generally done in 3D, specific gestures have to be thought of in order to provide clutching mechanism or to disambiguate which object should be moved and when. Therefore, past approaches relied on a combination of unimanual and bimanual gestures. Let's start with data and cutting plane manipulation techniques. In this first example, surgeons can use one hand to manipulate patient data in the operating room, but using a single hand limits what can be done in terms of data manipulation and analysis, although it seems realistic during a surgery that a doctor is not going to take their time to perform a full data analysis. To provide more data manipulation possibilities, having bimanual gestures is a good alternative. For instance here, they use the number of hand and the way they are presented, clenched fist or open palm, to distinguish between several manipulations such as zoom and rotation. More expressive gestures can also be used, of course, and some of the approaches we surveyed decided to look at this. One notably defined a gesture to crack open a dataset instead of using cutting planes in order to look at the internal structure of the data. We overall did not find a lot of different techniques, but since the number of papers that we found with gestural interaction was also smaller, this seems to make sense. Unfortunately, our survey did not uncover a lot of approaches to manipulate visualization widgets. While most of the developed applications that we have found for the first task of data manipulation do provide the ability to select some visual widget to browse through several 2D slices, for instance, we only found work proposing to measure the distance between 2 points, or to find specific values in a dataset. Similarly, we did not uncover a lot of work addressing 3D data selection beyond some quite basic techniques. One is the manipulations with the hands of predefined selection primitives, such as the cube visible here. Beyond this rather simple and not always convenient selection mechanism, brushing with gestures have also been proposed, as well as annotating directly with one's hands. This approach seems to more directly leverage the benefits of media interaction and would probably be very interesting to study further. So to conclude on media gestures, I would argue that very often the choice between interacting with a single hand or two hands will be constrained by the application domain itself. Media gestures have very often been investigated in a medical domain for obvious reasons around the sterile environment, right? But beyond this, the inherent expressiveness of media gestures shows promises for 3D visualization tasks. So we have now quickly surveyed past work on touch, tangible, and media input to facilitate 3D visualization tasks. Each paradigm shows interesting advantages. Touch is very good and natural to provide constrained interaction and easy to access widgets. Tangible interaction mimics real-life interaction, can sometimes be malleable and provide less generic cut-through data. Besides, tangibles are also very intuitive to provide 3D data / point selection and annotation. Finally, media gestures can be extremely expressive and allow users to stay in a sterile environment. All of these benefits can be combined through hybrid interaction techniques. Surprisingly, such hybrid interaction paradigms have received very little attention according to our survey. Let's review some of the approaches that we have found. Let's start with view and object manipulation techniques. To provide hybrid interaction, mobile devices are particularly interesting. They are nowadays capable of tracking their own manipulation, and they readily provide a touchscreen. Some approaches propose to combine free and intuitive manipulation of the mobile device to potentially constrain touch manipulation. Data in connect planes can therefore be separately manipulated in that way, as you can see here. Other researchers have imagined specific devices that would offer tangible and touch affordances, as you can see here, so that the cube can be moved as a tangible device, but you can also touch the surface to use it as a touch device. Most of the approaches that we found for data manipulation propose to combine touch and tangible interaction through off-the-shelf devices. What about visualization widgets now? When it comes to manipulation of visualization widgets, researchers have proposed again to rely on combinations of touch and tangible interaction from a mobile device, or to make use of specifically designed tangibles combined with touch surfaces, either mobile devices or touch table. You can see here one device that was designed by researchers in order to interact on top of a tablet. Again, the pool of technique we found for visualization widgets manipulation is extremely small, unfortunately. What about 3D data selection? Here again, the idea to combine touch and tangible interaction is interesting. One way to overcome the inherent limitation of the 2D input provided by the tablet is to move the tablet to extend the lasso into 3D. So you can see here the lasso being drawn, and the movements of the tablet are going to extrude this 2D shape into a 3D one that will provide the selection volume. Another way, as imagined here, is to use ray casting from the fingers in order to select what is within the manipulated cube. It is not surprising that most of the approaches that we have found rely on a combination of touch and tangible input, which are readily available with mobile devices. Some other approaches have worked to combine voice input to touch or tangible input to validate commands, for instance, but overall the vast majority of hybrid interaction approaches were combining touch and tangible manipulations. So we have now briefly surveyed the work on interaction techniques for 3D dataset, but what can we learn from the exploration of all of these approaches? The breakdown of past research on interaction paradigm and visualization tasks that you see here is interesting, but the choice of interaction might also depend on what technology is used to render the dataset, or in what environment. We therefore also propose a table breakdown that includes all of the output environments and a combination that you can see here. The color is used to encode the output used for each paper we surveyed. And to facilitate reuse and analysis from the community, we made the data easily available on our OSF repository, so you can filter and further analyze the papers that might seem relevant to you without having to click on many different references and scroll through the paper countless times. When possible, we also link to open access versions of the papers too. But let's come back to this table quickly now to try and get some interesting insights. One quick finding is that tangible interaction and touch interaction, to a certain degree as well, have received a lot of attention, while other interaction paradigms, such as media gestures, seem to not have been explored as much, although they seem to present interesting advantages as well. But beyond this, what is really striking, I would argue, is the lack of focus on manipulation of visualization widgets. This could be partly explained by the fact that the HCI community is not as likely to be aware about the needs to focus on this as we are in the visualization community, for instance. But more interestingly, with some co-authors, including a researcher in fluid dynamics who has also used the system that we developed, we have argued in the past that the fact that researchers in VIS and the fact that they don't provide a system supporting all the needs of domain experts that would integrate also in their workflow could very well explain the lack of adoptions of our tools and techniques by domain experts. Another exciting venue for future work lies in the use of interaction to help inform the public. Interactive exploration of data is beneficial to experts, but also has been argued to help in outreach and science communication overall. However, only a couple of the works that we have surveyed focus on providing intuitive interactions paradigms that could be used in the context of public activities or places to communicate about scientific discoveries, such as museums. On this topic, my co-author Anders would be happy to explain the idea of Exploranation and all the initiatives done at the Visualization Center in Norrköping, where Anders has been actively working. Another document we put online for people to explore is the breakdown of which paradigms were used by hybrid interaction techniques. I have mentioned it multiple times, the focus on tangible is logical. However, other combinations should surely be investigated, and we hope that we have managed to stimulate interest in this regard. What about tangible and immediate gestures, touch and voice, or even a combination of more than two paradigms? This is rarely a vision, and one can argue that it should be. Finally, one last challenge and avenue for future work that we argue for is evaluation. This is particularly relevant for spatial datasets and research around them. We often have to focus on specific domain and therefore ask for inputs or evaluation from domain experts who are, by definition, not many and not necessarily available for long and repetitive evaluations. I assume that many of you are familiar with the Believe workshop on going beyond time and error in visualization techniques and their evaluation, but I guess it's always good to point to this initiative now anyways. We found that some papers relied instead of on use cases or on in situ evaluations, for an example with surgeons during real procedures, which I think is extremely promising and exciting. Some researchers in the field have argued before that perhaps we should not rely solely on evaluation to accept and reject papers, and that sometimes publishing without evaluation would help spark some creativity in the domain. I would tend to argue that it would be fine to do so as long as authors don't make claims about the efficiency of their technique. Similarly, it was extremely difficult to find mentions in all of these papers of which system were successfully adopted by domain experts. And newspaper pieces often report that AR/VR visualization softwares are helpful, but they rarely cite the work that we do. And making a piece of software robust enough for domain experts is time-consuming, and considering the whole publish or perish paradigm in academia, it is therefore unlikely that researchers will spend tremendous efforts to make it happen, as they would not get any direct benefit for it career-wise. But in the medical field, for instance, doctors can report on unusual cases with what is called case reports. Perhaps we could just adopt case report to mention successes and failures in trying to develop for domain experts. That might be a way to solve this issue by giving incentive to spend more effort in developing for domain experts, because we then provide the opportunity to publish about it. One last explanation of why our work might not be adopted is the fact that the code we have is not necessarily shared by default. With co-authors outside of HCI and visualization, last year we argued for the benefits of open science quite strongly while looking at COVID-19 research, at its lack of transparency and what it led to. While in our field the consequences of a lack of transparency are surely not as dramatic, it would still be beneficial to make it a habit to link to source code for others to use, reuse as baseline for studies, or for fellow programmers to improve on, and therefore perhaps foster adoption of our techniques by domain experts or other users. On the topic of open science, the preprint of our paper contains a link to the open access version of all references whenever possible, as you can see here highlighted in bold. Clicking on open access should lead you right away to a non-paywalled version of the reference. All the credits and references from this talk are detailed here, and the list will be posted on our OSF repository. So that's it for me. Thank you very much for your attention. You can find the paper and all our materials online. We'll be happy to take your questions now.